Now we're going to look at a protocol that you have to learn for your test. This protocol is real important for two reasons. One, it's how we put an amine group on benzene. It is not known how to do that directly, so don't pretend it is. It's a multi-step process, clearly two steps. Nitration followed by reduction. And later, you're going to learn this new thing called diazotization that can lead to a lot of new groups on benzene. But they don't go in addition to a group that was already on benzene. So we're not going to talk about directors here. We're just replacing this N triple N plus. It's called a diazonium ion. Diazonium ion is unstable if it's warmed up to greater than 5 degrees Celsius. Oh, wow. Okay, good to know. Watch out. So when you make it, you better make sure it's cold. And the easiest temperature to maintain that's cold is 0 degrees Celsius. You surround your reaction with an ice bath. Easy to do. Well, I might as well give you the chemical since I'm in that box. NaNO2. NaNO2 is NO2 minus. It's called what ion? NiT. R. Nitrite. So I have sodium nitrite. I have HCl excess dissolved in water. There you go. And that mechanism is fun. It reminds me of the Wolff-Kishner a lot. Remember the Wolff-Kishner? You're going to see some similarities there. Except Wolff-Kishner's in base and this one's in acid. Okay, nitration we did. I think it was the first thing we did today, wasn't it? H2SO4 was one of the chemicals. Yeah, HNO3 is another chemical. That wasn't the first thing we did today. There it is. HNO3, H2SO4. You are correct, and that's going to puts a nitro group on benzene, right? Nice nitration. Getting rid of you. Go to the end. Went too far. Okay. So H2SO4 and nitric acid. H2SO4, HNO3. Reduction. Any ideas? NaNO2? No, that's going to make an amine into a diazonium ion. This reduction. Yes. You can use lithium aluminum hydride followed by HCl. I'm going to tell you right now, you need to know 3 other versions of this reaction because it's a very difficult reaction. And the first one you try in the lab never works. Never. So sometimes you got to try like 20 different reductions of nitro group to make it work. And it's that important. You've got to find one that works. Because nitros, they're an important group. But amine groups are an incredibly important group. I mean, every psychoactive pharmaceutical agent has an amine attached to benzene pretty much. Well, I got carried away there. But there's a lot of them, okay? What do we got? We're going to do H2 and platinum. So other reductions that can work. Good thing this is a lecture course, right? Because everything in a lecture course works. It can work. So H2, comma, PT. That's one. H2, comma, nickel. And it's a very special nickel. Some guy put his name on it. Rainy nickel. It's just how the metal was processed. It's an engineering thing. There's tin, comma, HCl. There you go. So 4 reductions there. Notice sodium borohydride is not on the list. Doesn't work. Doesn't work. So other reductions that can work. Then you do a diazotization. And the substitution reactions happen when you warm these reactions up to room temperature. Every one of them needs to be warmed up so the diazonium ion breaks apart. So RT is a very common short form in chemistry. You do not have to explain it. But on this page, I better at least explain it one time. Room temperature. And you've got to memorize these chemicals. For the BR one, it's a combination of, what color are we going with here? Green. Copper +1 bromine with HBr. 2 sources of bromine. This one also works with CuCl, HCl, giving benzene with Cl. There you go. But it doesn't work with an iodine doing the same. The iodine one, you're just going to use Ki. The reasons for these things are beyond the scope of this course, as they say. There's radicals involved, they suspect, in these mechanisms. And iodine makes nice radicals by itself because it's so big and fuzzy. Bromine needs help by way of the copper. And what about going to the left? Cyanide. It's similar. You use CuCN, but don't use HCN. KCN doesn't work. Cyanide's more like a halogen than it is like an iodide. Cyanide is pseudo-halogen, they call it. And you can't use HCN for health reasons. I wanted to generalize this one and use the same, but I can't. HCN, I mean, that's responsible for hundreds of thousands of deaths during World War II. Auschwitz. Yeah, not good. They were making HCN and putting it into these showers and killing people. It's terrible. It's dangerous. So you use KCN, like she said. I dismissed her because it wasn't the first one in my mind. But we need it. So it's good.
How is the world not talking about it?
That's a great question. Beyond the scope of this course. Okay. Yeah. The fluorine's just a weirdo. It's not related at all to anything on this page. You're gonna say, okay, I wouldn't have figured that one. It's called fluoroboric acid. HBF4. Somebody can open their book. Okay. Fluoroboric acid. BF4 minus is the anion and H plus is the cation. And this one's just basically warm it up with water. That would be the easiest one. You want to see how it's easy? Look at the ingredients to make the diazonium ion. What's AQ? Water. There's more water than anything. You do it to make the diazonium ion, then you take away the ice bath. What happens? The water reacts and does this. You're not responsible for any of these mechanisms on the bottom. Okay? Isn't that good news? Yeah. But the one to make the diazonium we're going to do is activity 6. This one looks bizarre. Why the heck did you start with benzene so you could end with benzene? That's crazy, right? Think about it. You'd probably be fired. That's benzene. That's an H, not a CH3. That's benzene, just like we started with benzene. I will give you an example right here about using this protocol to get rid of the nitrogen and putting halogens where you want them meta to each other. A lot of talk. This one's just H3PO2. What? 2. Write what you say, Dr. Whitaker. PO2. Okay. And it was H3. Losing my mind. There. What's that called? There's a series here, H3PO4, H3PO3, H3PO2. Hypophosphorus acid is correct. It doesn't even behave like an acid. That's a lot of pHs. Oh, wow. Okay. And there's that. Here's something on the bottom of the screen just to show you getting rid of the nitrogen might be something you're interested in. Right now, I'm going to start with the nitrogen here, and I'm going to go Br2 excess with, just to be safe, Fe Br3. And what happens is the nitrogen has a lone pair, right? That stabilizes cations during electrophilic aromatic substitution. Okay? So the first one's going to go where? Ortho or para? Ortho's got a little bit of steric hindrance. I'd say it's a little slower than the other one. Para is the first bromine. Next bromine is ortho. Third bromine is the other ortho. End of story. I want to put as many bromines on all the ortho para positions as possible. And that puts them here, here, and here. And bromine's now blue. And then I'm going to do this protocol here. Watch this. And you should be able to predict the result. 1, NaNO2, HCl, excess, AQ, 0 degrees Celsius. Step 2. Step 2, purple. H3PO2, RT. Talk to me. NH2's off, and that's it. Bromines stay. But the interesting thing is, what's the relative positioning of the bromines to each other? Whoa, that was interesting. I think just move the benzene. The whole cheese to the separate? This thing is torturing me. You saw me drawing it, right? Okay, boss. Okay. There. They're meta to each other, yes. Thanks for waiting. So if you tried to put the BRs directly on benzene, do it this way. Br2, FeCl3, excess. If you had to put 3 bromines on, first one goes anywhere. Where's the next one go? Para. Where's the next one go?
Nowhere.
Nowhere. Okay. Well, they are ortho directors too, right? So if you want to put a third one on, it's got to go there. But that's also meta to another one, so you are going to have trouble. Okay? But that's not what if this is what I wanted, say you were told I want to make that. This is not an approach that you can use, is it? That's the message I want you to have right now. If you want to try to make that, you can't put the bromines on directly. You got to take advantage of the fact that NH2 is the strongest OP director possible. Director possible. So putting all the groups ortho and para puts the bromines meta to each other. There's the picture right there. Here's the two ortho positions and the para position to the NH2. And then you eliminate the NH2. Sorry, I rotated the molecule. But there's the story. See if I try to rotate it. I've had trouble moving that molecule a lot. So that's good. I just rotated the bromines. I apologize for that. I rotated the molecule 60 degrees to get from here to here. I didn't need to do that, but I did. And if your objective is to make 3 bromines meta to each other, you got to follow this protocol. If this is your objective, then you can do it this way, but it wasn't my objective when I wanted to make that. So that's that. And then on activity 6, we're just going to flip this thing over. Oh, we're not ready for that yet. Yes, we are. I didn't copy the most recent one. Yours has a comment here, right? The comment on yours says, or doesn't? Flip this over and do the mechanism for which of these steps? Diazotiazation. So we're on activity 6, we're going to do exactly that. There's the reactant. There's more reactants. There's the product. We're going to get on it right now.